So today we're going back to atomic theory. Right? We talked about atomic theory at the beginning of the semester, and then I said, all right, we're going to take a pause from atomic theory until week 13, and then we'll come back to atomic theory. So here we are, week 13. We're coming back to atomic theory. Today we're going to look at Bohr Model, and if we have time, we'll start talking about quantum model. If we don't make it to quantum model today, we'll do quantum model on Friday. All right, so just a review of the models of the atom, right? There's Thomson, Rutherford, and Bohr. We talked about these first week of the semester. Right? Thomson had the plum pudding model, the solid sphere. That's positive with the negatives dispersed throughout. Rutherford model is the one you see on the well-known TV show. Right? You've got the solid sphere, the nucleus, and the electrons in random paths. Bohr's model, the planetary model, even though the planets don't orbit in circular paths, that's okay. You got the nucleus with the electrons in these fixed paths. And then the quantum model, which is the currently accepted model of the atom. Right? We'll deal with that one on its own lecture. So Bohr model, right? This is where we stopped at week 1. I said this is where we're going to end, and we'll come back to it in week 13. So the Bohr model is not the currently accepted model of the atom. A lot of high schools, especially, teach that the Bohr model is the current model of the atom, and you draw your little circles and your little rings, and you draw a number of dots. Do you remember doing that in high school, physical science? Right? It's not the currently accepted model of the atom, but studying why is really important prerequisite knowledge to understanding the quantum model, which is the currently accepted model of the atom. So we're going to do a little bit of physics. So if you guys have taken physics lately, this might probably be a little bit of a snooze fest for you. That's okay. So let's talk about the electromagnetic spectrum, which is a continuum of energy, right? So the light that we're visibly able to see is in this range right here, right? You can't see radio waves, you can't see ultraviolet radiation, right? We are only able to see light in this little tiny sliver of the electromagnetic spectrum. Excuse me. So let's talk about some properties of waves. Wavelength, which is the Greek letter lambda, lowercase lambda, is the distance between two crests, right, or two troughs. Take your pick. This is going to be the wavelength, right? This is going to be the wavelength. This is going to be the wavelength, right? That's the distance between two crests or two troughs. And then the frequency, which is the Greek letter nu, and that's lowercase as well, is the number of waves passing in a particular time frame, right? So if you're standing at the end of a dock and you're watching the waves come in, and you count, okay, 5 waves pass in 1 second, right? That would be the frequency. And then the amplitude is the vertical distance from either the middle to the crest or the middle to the trough. Like I said, this is probably review for you guys. It's not getting caught up on some vocab. Wavelength, frequency, and amplitude. We've heard these words before, right? Yes? Yes, yes, yes. Okay, so amplitude and wavelength are 2 words that students misuse, right? So what's the difference between amplitude and wavelength? They're not the same thing, right? These 2 waves have the same wavelength, yes, but they don't have the same amplitude, right? They don't have the same height. So just make sure you understand, because this is one that students really mess up a lot, amplitude and wavelength, right? Amplitude is this distance versus wavelength is this distance, okay? So pick the statement that is true regarding these 3 waves. The 3 waves have the same wavelength. The 3 waves have the same amplitude. The 3 waves have the same frequency. Which statement here is true? Which one? B. Right. Oh, they have nothing in common. B is the correct answer, right? They have the same amplitude. They all have the same height. Now, there's no scale here, but you could just qualitatively tell by looking at this. They have the same height, but they definitely don't have the same wavelength, right? Bigger wavelength, smaller wavelength, much smaller wavelength. Okay, so what is an electromagnetic wave? An electromagnetic wave has an electric field component, right? Electric field component, and a magnetic component. And they have the same frequency and the same wavelength. So as the name implies, electromagnetic, right? It's got an electric field component and it's got a magnetic component. So if you could visualize one like this and one like this, kind of tilted on each other, they have the same frequency and then the same wavelength. And so the speed of light, which I'm sure you've probably seen before, we're going to round it to 2.99 times 10 to the 8th, Okay, you're not going to have to carry out all these sig figs. And we represent that with lowercase c. Okay? And all electromagnetic radiation travels at the speed of light. That's convenient for us, right? All electromagnetic radiation is traveling at the speed of light. The relationship here is speed of light is equal to, what does this stand for? Wavelength, and what's this? Frequency, right. Now the wavelength needs to be in meters, okay, so make sure that it is in meters. So for instance, if I give you a wavelength in nanometers or picometers, make sure you convert it to meters. And frequency is in hertz or reciprocal seconds, right? So if you've seen hertz in your physics classes, maybe that's what you'll be saying tomorrow after your test. Oh, this hertz, different kind of hertz, right? Hertz is the same thing as seconds inverse, 1/seconds. So wavelength is in meters, frequency is in reciprocal seconds. That way, when you multiply meters times 1/seconds, you get meters per second as the unit for the speed of light. And the speed of light's a constant, right? We don't factor it into sig figs calculations. We're going to use 2.99 times 10 to the 8th. You do not have to carry out all these decimal places. Feeling good about this? Physics stuff. So if you've taken physics or even physical science lately, it's probably a review. So let's do this one together. A laser used in the treatment of skin lesions has a wavelength of 532 nanometers. What is the frequency of this radiation? So wavelength is given. We want to know frequency. What other piece of information do we need to have? We need to know the speed of light, which you are responsible for knowing. What is it? 2.99 times 10 to the 8th. Right. But before we do any calculations, we've got to convert nanometers to meters, right? Because speed of light is in meters per second. And if I plug in nanometers, well, then my units are going to be a disaster, right? Because then I'll have crazy units with involving nanometers and meters. So you have to remember back to the very beginning of the semester, my metric prefixes. Oh boy, they come back to haunt you, right? 10 to the 9th nanometers in 1 meter. You can remember nano like 9, right? 10 to the 9th nanometers in 1 meter. So you got to convert nanometers to meters first. Now we can do our arithmetic, right? If frequency times wavelength is equal to the speed of light, then all I need to do is rearrange. Okay. Meters per second divided by meters. Meters go away. I'm left with hertz. You can also write your units as seconds inverse. We're keeping 3 sig figs because the wavelength was 3 sig figs. Remember, we're using speed of light as a constant, so it's not calculated as part of our sig figs. Did everyone see how we did this? You ready to try one on your own? Reviewing some physics. Okay, you do this one. A laser used in eye surgery produces radiation with a wavelength of 6.4 times 10 to the second nanometers. What's the frequency of this radiation? I'll pause the recording for a minute. All right, let's look at this one. So we're calculating frequency, so we should know what our units are. What are the units of frequency? Hertz, right? You could also write it as 1/seconds or seconds inverse, that's fine. Right? But can we use nanometers in this calculation? No, we have to convert it to meters, right? There are 10 to the 9th nanometers per meter. Now we can plug it into our relationship that we just discussed, 4.67 times 10 to the 14th hertz. Is that a reasonable answer for a laser? Yes, that is. Questions on this one? So we are using the relationship speed of light is equal to wavelength times frequency. All right, try this one. Our radio station here on campus is 89.1. If you've ever wondered where those numbers come from, they're not arbitrarily chosen. What those numbers are is the frequency of the radio waves. Right, so if you're listening to a radio station, 101.4, I just totally made that up. I don't know if that's even a real radio station out here. Right? The number is the frequency in megahertz. So what's the wavelength, and I want it in meters, of our radio waves? And then based on that conclusion, would you say that these are dangerous waves or safe waves? And I've told you that a megahertz is 10 to the 6th hertz because we didn't deal with the mega prefix at the beginning of this semester. All right, let's talk about this one. So megahertz, obviously, we need to convert to hertz, right? Because if we plug in megahertz into our relationship, our units will be a mess. So we need to convert megahertz to hertz, and then we can solve for wavelength, which will come out in meters, right? We don't need to do anything to get our wavelength to be in meters. So you convert megahertz to hertz. So that would be 8.91 times 10 to the 7th hertz. And then when we plug it into our speed of light is equal to wavelength times frequency, we get 3.36 meters. 3 sig figs. Would we conclude that those are dangerous waves based on that wavelength or not? I mean, it's usually you look at the frequency to determine danger zone. But even if you look at the frequency, would we conclude that those are dangerous waves or safe waves? Give you a hint. We broadcast them here out into the world. So I would hope that they are safe, right? But you can also look as a comparison, look at our previous problem. This was a laser for eye surgery. It had a frequency of 10 to the 14th hertz and a wavelength of 640 nanometers, right? Versus a wavelength of 3 meters and a frequency of 10 to the 7th hertz. So yes, those would not be considered hazardous waves. Just the fact that you think about the fact that they're going through the air right now, you'd sure hope they're not. Okay, so at the beginning of 1900s, turn of the century, physicists are kind of arrogant. They thought they had it all worked out. They're like, okay, we can stop studying physics now because we've written the book. We're done. Early 1900s, beliefs about nature of matter. Matter was thought that particles had definite mass, know their location, right? I could point to that bottle of water and say, yep, there it is. Energy was light, and light was energy. In other words, those two went together. Energy and matter were mutually exclusive. In other words, matter could not emit energy, etc. Which is what I just said. Matter cannot absorb or emit energy. Now, we all know that that's not correct, right? But we have the advantage of being in our current time versus 1903. So here are some beliefs about early nature of matter. Waves are waves, particles, particles. So if we're looking at wave behavior versus particle behavior, right? If I'm looking at wave, when a wave enters a medium like water, it gets refracted some angle, right? Whereas if I throw a rock into a pond, it just keeps on going, right? There's no refraction there. And then if you're looking at waves, right? If I've got waves coming in and then there's a little hole, right? They do this motion to make those crests. You can think about waves on the seashore, right? And then there's a little hole. Go out in those crests. Whereas if I'm shooting beams of particles, these ones stop and these ones just keep on going straight, right? Those are beliefs about waves versus particles. But we know, we have the advantage of where we are in the timeline, of knowing that belief about waves, matter being separate from energy, can't be true, right? Because if we just look around, how can matter emit light? Just go home tonight if you have a stove with coils, turn it on, watch it get red, right? Or you turn on a light. Oh, okay, there's light coming out. Well, something's going on here, right? There is a relationship between matter and energy. So if our model doesn't match reality, we need to rethink our model, right? And so if you've taken physics lately, you probably spent a lot of time talking about the photoelectric effect, which I'm not going to spend a whole lecture talking about. Just want to let you know about the findings, the major findings. When light strikes a metal, so here's light coming in, it's striking a metal, right? The metal ejects electrons, which you can study in an electric field, right? And that's surprising. Think about why, because light doesn't have mass, right? If I throw a rock at metal and something comes off, okay, well, the rock has mass, so it makes sense that something would get kicked out. But light doesn't have mass. So why would light cause electrons to get kicked out? That doesn't make sense. Based on what they knew at the time, right? So that led to the conclusion, okay, light must behave like it has mass. So what does it teach us? It teaches us that light, which is part of the electromagnetic spectrum, so in other words, light and all electromagnetic radiation, is a stream of particles, in quote marks, which we call photons. And the energy of a photon, E, we represent that as capital E, is equal to Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds, times frequency, which is in hertz. This is the relationship between energy and frequency. Energy is in joules, H is Planck's constant, and V, that's the Greek letter nu, right, lowercase nu, is frequency in hertz. And if you are majoring in chemistry, which I hope you all are, that'd be great. Right, you'll go on and you'll take physical chemistry and you'll understand where Planck's constant comes from. I'm not going to derive Planck's constant for you. I don't think it's necessary to your knowledge and understanding at Gen Chem level. But if you do decide, hey, I want to be a chemist, you'll spend a lot of time talking about where Planck's constant comes from when you take P-Chem specifically. There's a little bit to lighten up the mood. Photon checks into a hotel. Do you need help with your bags? What did the photon say? Anyone get prepared to be laughing? Like, are you ready? Holding on to your sides because they're about to split. I'm traveling light. You got it. Okay, so the implications here. Matter has both wave and particle properties. So light behaves as if it has mass. Right? If you look at how light behaves in deep space, we pull toward black hole. The wavelength is the primary influence on photon behavior, right? Because it's behaving as if it has mass, but it's so small. So if we're talking about an electron, right? The wavelength is the primary influence on its behavior. And we have wave properties too, right? I have wave properties, you have wave properties. But our mass is so much greater than our wavelength, right? So that means that our mass is the primary influence on our physical behavior, right? So I wouldn't use quantum mechanics to describe my motion or my position. That doesn't make sense because I'm a large macroscopic object, right? I would have to use quantum mechanics to describe the position or behavior of an electron. All this is leading up to quantum mechanical model, which we're not there yet. But there's the relationship that we just learned. Energy is equal to Planck's constant times frequency. So let's do this one together. Calculate the energy of a photon with a wavelength of 5 times 10 to the 4th nanometers. That's in the infrared region. And then calculate the energy of a photon with a wavelength of 52 nanometers, which is in the UV region. And then we can compare those results. Just before we even get started, does anyone know if you had to choose which form of radiation to be exposed to, infrared or ultraviolet, which one would you pick? Does anyone know? You'd pick infrared. Let's talk about why. So if we're going to calculate the energy with a wavelength, we have to do a two-part calculation. This is a two-part calculation. Because if I want energy, energy comes from this equation, right? Planck's constant times frequency. Yes, that's the equation I need to plug into. But I didn't give you the frequency. I gave you the wavelength. It's unconvenient. Right? If I want to know the energy of the photon, first thing I have to do is I've got to calculate its frequency, because this is the equation I'm ultimately going to be plugging into. Does everyone see why this is a two-step problem? Because I have to know frequency in order to plug in to get energy. So how can I get frequency? Well, we just talked about where I could get frequency just a second ago, using the speed of light and the wavelength, right? So we convert nanometers to meters, which we have to do, right, because nanometers, 10 to the 9th nanometers per meter. And now I can plug it in and get frequency, right? If speed of light is equal to wavelength times frequency, then frequency is speed of light over wavelength, right? Because meters cancel, I'm left with seconds inverse, which is hertz. Now that I've got hertz, then I can plug it into my energy equation and get the energy. Does everybody see why you've got to do two steps here? The two-step problem, right? Because if I say, here's the wavelength, what's its energy, you have to know frequency. And the only way you can get frequency is through this relationship right here. Now we can plug in energy is equal to Planck's constant times frequency. So Planck's constant, 6.626 times 10 to the negative 34 joule seconds, times my frequency, which is seconds inverse, right? Seconds and seconds inverse cancel, so it leaves me with a energy in joules, 3.96 times 10 to the negative 21st joules. That's a small number compared to some of the other joule calculations we've done lately with thermocam, right? Those are all kilojoules. So this is a different scale that we're looking at here. Does everybody see how we did this? Does this make sense? Now that was just for photon with wavelength of 5 times 10 to the 4th nanometers. How will I do part B? Is part B a one-step or a two-step problem? It'd be a two-step problem as well. Right, what would I do first? Convert wavelength into, oh, right, gotta convert to meters. And then what would I turn my wavelength into? Frequency, right? And then I would plug into my energy relationship. Does everybody understand how we did the first one? Wavelength of 5,000 nanometers. All right, let's do part B. 52 nanometers. Again, we've got to convert nanometers to meters. And then we're going to plug it into speed of light is equal to wavelength times frequency. So I get 5.8 times 10 to the 17th hertz. And now I take that value as my frequency, plug it in here. Planck's constant is constant. So now I just multiply those two numbers. And I get 3.8 times 10 to the negative 16th joules. 2 sig figs this time, right? Because I had 2 sig figs here. I had 3 sig figs on the first one. Does the speed of light or Planck's constant factor into sig figs? Do they factor into sig figs at all? No, right? Because they're constants. They're not measured values. Does everybody understand how and why we did part B the way we did? Okay, so now let's compare. Part A, we got 3.96 times 10 to the negative 21st. Part B, we got 3.8 times 10 to the negative 16th. Right, so we're looking at our electromagnetic spectrum. Right, here's the frequency 10 to the 16th versus 10 to the 12th. Right, so the ultraviolet radiation is something you want to avoid. Right, that's a higher energy. 10 to this negative 16th is a bigger number than 10 to the negative 21st, right? That's higher energy. That's more energy going into you if you're exposed to ultraviolet radiation versus infrared radiation. Makes sense? Makes sense? All right, so you try this one. Blue color and fireworks. You're heating copper 1 chloride at 1200 degrees Celsius. Does that temperature factor into our calculations? Just extra information. It emits blue light with a wavelength of 450 nanometers. What's the energy of photons at this wavelength? So make sure you're able to discern important information versus extraneous information. Temperature is not being a factor in our calculations here at all. I'll pause the video and let you think about this one. All right, let's go over this one. So temperature isn't a factor. And the identity here isn't a factor either, right? This is the first time where you don't care what the identity is. You don't care that it's copper 1 chloride. You don't care that it's 1200 degrees Celsius, which is really, really hot. What we do care about is the wavelength, right? So we have to do 2 calculations. I can't plug wavelength into my energy calculation because if I say, what's the energy? Well, wavelength isn't part of my energy calculation, right? So first I have to calculate frequency using speed of light is equal to wavelength times frequency. Solve for frequency, right? Speed of light over wavelength. Or you could just plug it directly in and then do the arithmetic. You'll get the same answer. And then, you know, carry out an extra decimal place because my final answer is only going to have 2 sig figs. So carry out extra decimal here so that you can round at the very end. I got 4.4 times 10 to the negative 19th joules. Did you? $4.24? Let me make sure that I didn't make a math error there. Yeah, I got it 6.626 times 10 to the negative 34 times 6.67 times 10 to the 14. 4.419 is what I got. Oh, for this one?
Yeah, I got 6.
Okay, maybe that's where it is. 2.99 times 10 to the 8 divided by 4.5 times 10 to the negative 7. 6.64.
Okay, I see.
Yeah, so I just rounded my answer here. Slightly inappropriately, 6.64.
Yeah, I accidentally put 2.9, not 2.99.
Yeah, that little thing, you know, just something real trivial. When the numbers are this small, can make a difference. So it still comes out to be 4.399, which would round to 4.4. Do you agree? Once we round it to two significant figures, it's still 4.4. Now, if we're keeping three sig figs, it would be 4.40. Okay, let's just do this one verbally. There's nothing to calculate. Using your knowledge of the electromagnetic spectrum, which form of radiation is more dangerous, gamma rays or ultraviolet rays? Does anyone remember where gamma radiation is in terms of the scale? Maybe you just know it from your life experience. Hopefully you don't have a whole lot of experience with gamma radiation. It's on one of the ends. Is it on the good end or the bad end, right? Radio waves are down here. Gamma is way down here, right? Gamma radiation is not something you want to be around, right? Radio waves, we broadcast them here on campus. If we were broadcasting gamma radiation, that'd be really bad, right? That's ionizing radiation. That's bad news. And you could always calculate, the energy. Now let's talk about the Bohr model, right? Bohr has this nice little nucleus in the middle, right? And then the nice pretty rings going around. Yes, that's what Bohr's model looks like. And so if we're looking at the Bohr model, N is the radius of that energy level, right? N is the radius of that energy level. So if we're drawing out the Bohr model, we're drawing out a sketch of the Bohr model, right? There's our nucleus, and then we've just got these nice circular rings, right? So this would be N equals 1, this would be N equals 2, this would be N equals 3, et cetera, et cetera, et cetera, okay? So according to the Bohr model, when N equals 1, that's called ground state. Okay, lowest energy, because it takes the least amount of energy to occupy ground state. I think the analogy I gave you back at the beginning of the semester would be like standing on the bottom of a ladder versus standing on the top of a ladder, right? Where do you have the greatest potential energy? Where would you get the most injured if you fell, right? Lowest energy is at ground state. And so energy level greater than 1 would be an excited state. So the further you are from the nucleus, the higher your energy. It takes more energy to stay at that energy level. So, electrons are like college students who are at their lowest energy level. I feel like that's just, electrons are like people. I don't think it's specific to college students. I think it's just people, right? We want to be at our lowest energy level. I know if I have the choice of, lounging around and relaxing or, I don't know, mowing the grass, I think I'm going to take lounging around, but probably should mow the grass. Right? I think this is analogous to anybody. But these states greater than 1 are when N's greater than 1, right? Ground state. But to get from N equals 1 to N equals 2, energy's got to be put in, right? Because for me to get up off the couch and go mow the grass, that takes effort on my part, right? So to go from N equals 1 to N equals 2, energy's got to go in. If I go back down from N equals 2 to N equals 1, that releases energy, which is what we're going to look at today in terms of our calculations. And you guys said you did that in physics? Yes? Good. Well, it's just a review. And if you haven't taken physics yet, the good news is that math's not hard. It's not hard at all. All right, so there's Bohr's drawing of the atom. Right, so this is what I just said. To go from ground state to an excited state, we have to add energy. So we're doing this in the form of heat, radiation, light, etc. And so that requires energy to go up in energy level, right? So here's kind of a picture. This is not from your current textbook. This was from a previous edition, right? There's n equals 1. That's the lowest state. You have to put energy in to get up to n equals 2, n equals 3, n equals 4, n equals 5, etc. Now, if you're going down, right, this is something my youngest son has discovered. He likes to go to the top of the stairs, and he's realized that if he drops a ball, it goes boing, 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 boing. Like, he really enjoys that. And it kind of stresses me out because I don't like to plan on the stairs. But if you are going down, right, that's energy that gets released, whereas to go up, that's energy that's required. Okay, so this is what I just said. When an electron falls from higher energy to lower, energy is released, and it's energy in the form of light. We can see that. And if it's light, for instance, blue versus green versus purple, right, those are all different wavelengths. So we can determine the wavelength and the energy based on the color. So if you did emission spectra in physics, you probably did. You looked at the little lines, you know, the colors of the lines. That's what you were observing here. You were adding energy, and that was exciting the electrons to a higher energy level, and then they were falling back down, right? And that was releasing energy. So the different colors correspond to different energy level transitions. Now, this is something I do with my intro chem students. This is an experiment that we do in introductory chem. We take samples of salts and we shove them in the Bunsen burner, and we get a nice pretty color. Maybe you did this in high school. This is an intro chem experiment that we do. You know, campus, but it's the same premise behind fireworks too, right? You're adding a ton of energy in the form of heat, and you're getting that energy level promotion, and then it falls back down, you're getting the light. And like I said, that's the physics experiment you probably did. Did you do that in physics? You had the little box with the sample in, it's really bright, you look at it through the thingamajig in front of your face and you can see the lines. Kind of had to close one eye sometimes. And that's the exact same thing again, just looking at different transitions, magenta versus purple versus blue versus red. What's the energy level? 6 to 2, 5 to 2, 4 to 2, 3 to 2, and then there's n equals 1. All right, and there's all the different elements in their spectra. So let's just answer this one together. Which value of n is a higher energy level? N equals 2 or n equals 4? N equals 4, right? That's the highest, that's a much higher energy level. What's ground state? Someone define ground state for me. N equals 1, right? N equals 1. Okay, which is closest to the nucleus? N equals 1 or n equals 4? N equals 1, right? That's ground state. So here's the energy level equation. If you did this in physics, it's probably a familiar equation. E of n, where n is the energy level, so it can't be 0, right? Because you can't have a 0 in the denominator. There's no such thing as a 0th energy level. So this is a value n greater than 1, greater than or equal to 1. So energy of the first energy level, second, third, fourth, fifth, etc., is negative 2.18 times 10 to the negative 18th joules. Now this is a constant, times 1 over n squared. So if n equals 1, it would just be 1 over 1. If it's n equals 2, it'd be 1/2 times this. If it's n equals 3, it'd be 1/3 times this. You get the idea? You just take this constant and divide it by whatever n is squared. And there is a negative in here, okay? That is a negative. That is a negative that's built into the equation. And the units here are joules. Okay, make sure you note that. The units here are joules. This is energy, so my unit is going to be joules. So if you're asking yourself, why is this negative? How come it's negative? Well, let's just think about it. If we think about 0 point, like where 0 is, that is the energy when the electron's completely yanked out, right? Just completely pulled away. So in other words, E can only be 0 when n is infinity. In other words, that energy level is so far away, it's completely out of the atom, right? And so the E is negative, right? Because you can also think about this as energy that we're applying. If I'm putting energy in, right? You can think of it that way too. Now, would I ask you to explain that on exam? No, but just for those of you who are curious. So let's do this one together. What amount of energy is required for an electron to occupy n equals 3 in a hydrogen atom? Well, there's our energy level equation. By the way, your reference page will contain this formula. You just need to know when to use it and how to use it. Okay, I'll give you all the formulas. So E equals Planck's constant times frequency, and speed of light is equal to frequency times wavelength. And I'll give you Planck's constant, and I'll give you the speed of light. Okay, you just need to know when to use all these equations. So energy of the third energy level would be negative 2.42 times 10 to the negative 19th joules. We're just dividing by 9. Do we agree? I want to see how to do this. Like I said, the math's not hard. Why don't you try this one? How much energy is required to occupy n equals 2? So this time we're dividing by 4. And again, that negative is part of the equation, okay? That's energy we have to apply to get to the second energy level, right? Do we agree? Now, here's an equation for changing energy levels. If I want to go from n equals 1 to say n equals 3, that's energy I've got to put in, right? And so delta, remember delta means change in, is delta initial minus final or final minus initial? It's always final minus initial, right? So energy is Planck's constant times frequency. We just established that a few minutes ago. It's also negative 2.18 times 10 to the negative 18th, which is a constant, joules, times 1 over final squared minus 1 over initial squared. So if I say, all right, I'm transitioning from n equals 4 to n equals 2, or I should say n equals 2 to n equals 4, right? Final would be 4, initial would be 2. Right? Now, sometimes you're going to get a positive number here. Does that make sense? Yeah, it does make sense. Sometimes you will have a positive number. So let's do an example here. Now again, I will give you this equation. You just need to know when and how to use it. So if energy is absorbed, electron moves up in energy level, delta E is positive. If energy is released, electron moves down, delta E is negative. So just the same as the definitions of exothermic and endothermic we talked about. So let's look at an example. Electron in a hydrogen atom moves from n equals 2 to n equals 3. What energy is associated with this transition? So there's our equation. Now we're not going to use Planck's constant times frequency. That doesn't make sense because that doesn't factor in energy levels. However, my second version of delta E does. Right? Final was 3, initial was 2. Do we agree? Any questions on this one? Right, this is energy that we're putting in. Why don't you try this one? Electron moves from n equals 4 to n equals 3. What energy is associated with this? I'll pause the video. Let's go over this problem. So n equals 4 to n equals 3. Which is final and which is initial? Right, n equals 3 is final, n equals 4 is initial. So that'll factor into how I plug into my equation here, right? Because if this is initial and this is final, right? Final goes first, initial goes second. So E is negative 1.06 times 10 to the negative 19th joules. Right? That's energy that that's being released. Do we agree? Makes sense? Are we all cool on how to interpret the sign here? It's just like when we interpret exothermic and endothermic. It's the exact same way. Now we can take this one step further, because guess what? If we know energy, then we can solve for frequency, and we can come full circle, we can plug it back in and solve for wavelength. Yay, isn't that fun, right? Because this is light that's going to be emitted, and each light's going to have a specific wavelength, specific color. So we could take this all the way. So we just calculated the amount of energy required to go from 4 to 3. Now I want to know what frequency of that light. What's the frequency of that light? So you just calculated energy. Now tell me what is its frequency. So you don't have to calculate energy again, because you just did. So tell me, what's the frequency of that light that's going to be emitted? Which equation do you use that relates energy and frequency? You use delta E is equal to Planck's constant times frequency. Right. So we're using this part of the equation. Right? Because we just calculated energy. Previous problem. This is a constant. There's nothing I need to do to get it. Right? It's a constant. So I just solved for frequency. Does everyone see why we chose that equation? So we're just rearranging. 1.6 times 10 to the 14th hertz. What if I said, what's the wavelength? Could you take it all the way back to where we began at the beginning of class? Go all the way from energy of some sort of transition to frequency to wavelength? Yeah, we sure could. So why don't you do that? What's the wavelength of that light? We just calculated frequency, 1.6 times 10 to the 14th hertz. Now I want to know what's its wavelength. So if you're feeling like you're at a very familiar spot, this is where we started. Came full circle. Always have to convert to meters, yes. But here, your answer is going to be in meters, because wavelength is going to get spit out in meters already. Because frequency is in hertz. So here you're solving for wavelength, which will come out to you in meters. Right, so here's the equation we're using. Speed of light is equal to wavelength times frequency. Speed of light's a constant. Frequency we just solved for. So to get wavelength, we plug in. Our answer is in meters, right? It gives it to me in meters, because my units are meters per second divided by 1 over seconds. So 1 over seconds, 1 over seconds, those go away. That leaves me with meters. Now, if I say, what's the wavelength in nanometers, you take that number in nanometers and convert it to meters and convert it to nanometers, right? So here are all our equations of importance. I'll give them to you. Okay, you just need to know when and how to use them. So this is calculating the energy of any energy level. This is change in energy level. This one's the relationship between energy and frequency. And this is the relationship between speed of light, wavelength, and frequency. Now I do want to talk about one quick thing, because it'll set us up for Friday's lecture really nice and neat. We had some real problems with Bohr's model. Right? There's some real issues with Bohr's model. One of the primary ones is that it doesn't work for anything other than hydrogen. So if you add second, third, fourth, fifth electrons into the mix, it's just a train wreck. And so we'll talk about this on Friday. There were some attempts, mathematical attempts, to correct it, but you just can't fix it. It's a broken engine. You had to go rebuild the engine, make something completely new. But the Bohr model did help us understand a lot of important information about the relationship between energy and matter, right? So Bohr model is not total trash. It's just not the currently accepted model of the atom. And one of the things that helped undo the Bohr model too was the wave property of matter. So de Broglie concluded that electrons behave not just like any wave, they behave like standing waves, which means they have specific frequencies that are allowed, and they have specific wavelengths that are allowed, I should say, right? So standing wave, you know, think like a sound wave, that's a standing wave. And so that's how electron wave behavior is acting. It's acting like a standing wave. So you can't have, you know, 3 1/3. That doesn't make sense. Whole number energies here. And I don't know the amplitude 0, which we don't really care about right now. And so if you took physics, you probably talked about these diffraction experiments. Did you talk about diffraction patterns in physics? Yes, no, maybe. Right, there's an electron diffraction pattern. There's X-ray diffraction pattern. Notice it's a pattern. It's happening the same way every time. And so there's just a lot of empirical evidence in terms of what we were doing in the lab that made the glaring problems with applying classical mechanics to the atomic level just kind of fall apart. So let's talk about those real quick, and then that's where we'll stop. It's a good ending place. So here's the original classical mechanics belief. Matter is matter, energy is like a wave. We already talked about photoelectric effect and black body radiation. Energy is in packets, only certain values are allowed, and then light behaves like it has matter. Energy of atoms is in packets, which is what we just set up here. And then emitted when electrons change its orbit. That's what atomic line spectra showed us. See, there's good old Bohr. And then de Broglie says matter travels in waves, and it's not just any old waves, it's quantized and it's specific. And then Einstein and de Broglie together, mass and energy equivalent, particles have wavelength, photons have momentum, right? So all of these experiments, you know, they didn't just happen one day, right? We're talking about a paradigm shift that occurred over a long period of time, which led us to quantum theory, which is where we're going to start on Friday. Okay, so quantum mechanical model of the atoms, our topic for Friday. Have a good day, and I'll see you tomorrow.